Hello everyone, welcome to JCE Connect series of lectures. So we have already started module number 5, that is design of beams. So in previous lecture we have discussed about the section classification, laterally supported beams, laterally unsupported beams, and the difference between laterally supported beam and laterally unsupported beams. So in this particular lecture we will be going to discuss different types of failure in beams, and next web buckling and web crippling, very important in the design of beam. Then the web buckling strength. So what is the strength in buckling and web crippling strength, and the deflection criteria. So these five things we are going to discuss in this particular lecture. So let us discuss about the types of failure in a beams. So there are four modes of failure of beams. The first one is the beam may fail, excessive bending failure. The beam may fail in excessive bending failure. And second, it may fail due to lateral torsional buckling. And the third, it may fail due to local buckling. And fourth, it may fail due to local failure. So again, the local failure means it could be fail by shear yielding of a web, or it could be failed by web may suffer a local crushing, or it could be failed by buckling of thin flanges of sections. So these are the some of the failures of failure modes of beams. Next, let us see one by one the excessive bending failure. So as we know, the bending is nothing but it's a state of stress occurs due to transverse loading. So always the beam will be loaded transversely perpendicular to its longitudinal axis. Because of the loading, the stresses will be induced in the beam, and because of that stress, because of the stresses, the beam may bend like this, and it may fail by excessive bending. And the beam is prevented from the buckling, and the component elements are at least compact so that they do not buckle locally. Means, so in such kind of beams, if they are failing excessive bending, its buckling is being prevented. And if the bucklings are prevented, so in this kind of sections could be of compact sections. So we have seen the section classification, what the compact section means. So that they do not buckle locally, and these kind of beams, if they are showing excessive bending failure, then it means the beam will collapse by plastic hinge formation. Means after bending they will form the plastic mechanism, then the moment distribution of the beam will takes place, then the sufficient hinges will be forming. After forming the sufficient hinges, the beam may fail. So this type of failure, what we call as excessive bending failure, in these kind of beams the buckling is being prevented, and so that there may not be any local buckling. So if the buckling is prevented means obviously these sections should possess the compact sections. Hence such beams will collapse by plastic hinge mechanism or plastic hinge formation. So next failure is a lateral torsional buckling. So what do you mean by lateral torsional buckling? This failure occurs by a combination of a lateral deflection and twist. Means, so you can look at this beam. In this beam, which is a before buckling, and this shows the after buckling. So lateral buckling means the deflection deflection of beam by sideward. So, and along with the deflection, it may twist also. That is called lateral torsional buckling. So, like this, look at this beam. So, this is the initial position of the beam before the loading, and once the loading is been done, because of the excessive loading, it has buckled sideward like this. It has taken the curved path. This is called a lateral buckling. Along with the lateral buckling, because of the couple moment acting on either side of the beam, this beam may get twisted. Hence, it is a combination of lateral deflection as well as twist. Hence, it is called as a lateral torsional buckling. This is also one mode of failure in a beam. See this failure, you can look at this picture. So in this picture, so the beam has failed because of the lateral torsional buckling. See, look, this beam, it has been twisted. This beam has been twisted and it has buckled sideward, that is deflected sideward out of the plane, and it has failed. And this failure, what we call as a lateral torsional buckling failure. And this failure can be avoided by providing a lateral bracing to the beam. So this type of failure can be prevented just by providing the lateral bracing to the beam. The next failure is the local buckling. So flanges may buckle. Local buckling, the flanges may buckle due to compression, and these flanges may buckle due to compression, and web may buckle due to shear. So as you know, in I section, if you take a I section, here I'll draw I section. If you take a I section, these flanges will be carrying moments, and these two flanges will resist the moment, and the web will resist the shear. Hence it is given flanges may buckle due to compression. Whatever the compressive load will be acting over the flange, it will resist those compressive loads, and web will resist the shear. See, look at this picture. So here the failure of the compression as well as web has taken place. Look at this I section beam. This is I section beam, and it is being loaded vertically. This beam is taking a load transversely. Okay, so this is the longitudinal axis of the beam, and the section is been taken, that is at section AA, and this is the section AA. So it has shown here the local failure on the flange of the beam. The ripples or the waves has formed because of the compressive stresses. So this type of failure is called as a local failure, a local buckling failure. And before reaching the yield stress, this flange has failed. And even if you take the section at BB, this is a section at BB, so it can be shown here, the section at BB, the part of the web has buckled or a crushed, you can call it as a crushed like this, and this failure what we call as a local buckling failure. And before reaching the yield stress, so these components or the elements have failed. This type of failure what we call as a local buckling failure. So look at this picture. So in this picture, the local buckling in the top flanges of the beam has taken place. See, the flange has buckled. It has buckled like a sinusoidal wave. The waves are formed like this. You can call it as a ripples. Okay, and web also buckled. This failure what we call as a local buckling failure. Even the web will get buckled under a concentrated load like this. Look at this one. The web has buckled like this under a concentrated load and under a support, see this has buckled. Okay, this failure what we call as a local buckling failure. So even uh, at the support, if you take at the support condition, support, there the web has crushed. Look at this figure, the web has got crushed. This is called web crippling. This also indicates the local buckling failure. Then this kind of failures can be prevented. So this type, whatever the failure is by local buckling, that is flanges may buckle or web may buckle, these can be prevented just by providing a web stiffeners and bearing stiffeners at the support. So the buckling can be prevented by providing the web stiffeners, and the crippling can be provided by just by providing the bearing stiffeners at the support under the point loads or at the support reactions. So if we provide the stiffeners for the web as well as for the flange, so this local buckling can be prevented. The next failure is the local failure. So local failure, these failures are likely in a short span or a deep beams. So these failures are likely in a short span or a deep beams. Like this, the shear yielding up a beam may takes place, or the crushing of web may takes place, or the buckling of thin flanges may takes place. So these type of failures what we call as a local failures. So these all three types of failure can be seen in this beam. So look at this beam. So you can see all the web has yielded and the crushing of web has taken place, then the buckling of flanges have taken place. So these all failures is shear yield of a web or a crushing of a web or a buckling up of thin flanges are being classified as a local failure of the beam. So how this local failure can be prevented or can be avoided, just by providing the web stiffeners, or the web stiffening can be done to avoid the local failure. And even regions surrounding to web holes may be strengthened by local reinforcement. Okay. And welding of additional plates to the flange can reduce the buckling, and this failure can be avoided. So these local failures whatever we have discussed, that is the shear yielding of a beam or crushing of a web or a buckling of a thin flanges, can be prevented just by providing additional plates to the flange, and even can reduce the buckling, and this failure can be avoided. The next is very important, web buckling and web crippling. So what do you mean by web buckling and web crippling? So before discussing about the web buckling and web crippling, so try to understand what you mean by bending and a buckling. So bending is different and buckling is different. Both are not same. So what do you mean by bending? So bending is a state of stress occurs due to transverse loading, and the buckling like this bending, so it's a state of stress occurs due to transverse loading. Always the beam is been subjecting to transverse loading. So like this transverse loading, and the load is been acting perpendicular to the longitudinal axis. Because of the transverse loading in this beam, the stresses will be induced, hence it is a state of stress. So on the upper side of the beam, the compressive stresses, so the fibers get contracted, and the lower side of the beam the fibers get elongated, and upper side of the beam fibers are subjected to compressive stresses, and the lower side of the beam fibers are subjecting to tensile stresses. Because of these stresses, the beam is being subjecting to bending. This is what we call as a bending. This is a state of stress and occurs due to transverse loading. Then what do you mean by buckling? Buckling is a state of elastic instability. It is a state of elastic instability occurs due to axial loading like this. Always this column is being subjecting to axial loading, and always the load will be acting parallel to the axis. But in case of a beams, the load was acting perpendicular to the axis. But in case of buckling, the load will be acting parallel to the axis. So it is this type of failure what we call as a elastic instability failure, and this will occur due to axial loading. So this is buckling, this is bending. Now let us discuss about the web buckling and the web crippling. So what do you mean by buckling and crippling? This is very important. So the beams, many times the beam could fail either by buckling and or by crippling, and how it can be prevented, let us see in this lecture. So what do we mean by buckling? So buckling due to high vertical stresses directly over a support or under a concentrated load, the beam web may actually crush or buckle as a result of these stresses. I'll repeat, due to high vertical stresses directly over a support or under a concentrated load, the beam web may actually crush or buckle as a result of these stresses. So let us look at this figure, and because of the excessive stresses, the web either to buckle or to cripple like this. Look at this figure. Due to high vertical stresses directly over a support, look at this, this is a support, directly over a support or under a concentrated load, the load is been acting vertically, a beam may be actually crush or buckle. Next figure, look at this figure, the beam, some portion of the web of the beam has crushed under the concentrated load as well as under the reaction. So these two types of failures, what we call as a buckling failure as well as a crippling failure. Okay, so what happens here, a heavy load, look at this figure, a load is been acting vertically downward, concentrated load, as well as because of the loading there will be a reaction at the support here. Okay, a heavy load or a reaction, heavy load or a reaction like this concentrated on a short length produces a region of high compressive stresses. So because of the loading as well as because of the reaction, a high compressive stress region will be formed in the vertical elements of the web, either under the load directly or at the support. Okay, either the load or the support. Hence a buckling or a crippling will takes place. And what happens away, if you take the away from the loading, so at this junction it will be stressed very heavily at the concentrated load or at the reaction point. So the beam web is being stressed heavily. If you take away from the loading point, the stresses will be spread very widely, but just under the load or above the reaction point, under the load or above the reaction point, they may cause web failure directly. These loads, if you take away from the loading, it will be spreading widely. If you take just under the loading point or under the reaction point, so it causes the web failure, and such failures what we call as a buckling as well as crippling failure. So crippling or the web has crushed, hence it is also called as a web crushing or web crippling. This is called as a web buckling or vertical buckling. Web buckling or vertical buckling, like this web buckling or the vertical buckling occurs when the intensity of vertical compressive stress, this type of failure occurs when the intensity of vertical compressive stress near the center of the section becomes greater than the critical buckling stress of the uh, web which is acting as a column. So this type of failure will occur uh, when the intensity of vertical compressive stress near the center of the section becomes greater than the critical buckling stress for the web acting as a column. And some of the experimental results which have indicated that the rolled steel sections, if you take the experimental results or some the what the so designers or the researchers said, uh, the test indicate that for the rolled steel beams the initial failure is by web crippling. The initial failure is by web crippling rather than by web buckling. Generally the first failure will takes place the crippling, then the web of the beam buckles. That is been indicated in some of the tests, so experimental tests. uh, and But if you take the built up sections or the built up beams having a greater ratios of depth to thickness of the web, if you take a built up sections or a built up beams, uh, if you take the greater ratios of depth to thickness of the web, the failure by vertical buckling may be more. So in those cases the failure by vertical buckling will be more probable than the failure by web crippling. So then this, what the preventive measures for this one? So the suggested solutions to this problem include the load should be spreaded in a wider area. Whatever the load is been acting, concentrated load or at the reaction point, this should be spreading over a larger area, in the larger area of the flange. And even you can provide the web stiffeners at the point loads. So to prevent this type of failure or this type of failure, the stiffeners can be provided for the web. We have to make this web stronger, hence the stiffeners can be provided to prevent these type of failures. Or whatever the load is been acting here, concentrated load, under the concentrated load or under the reaction point, the web can be stiffened, means strengthened, by providing additional plates. And also you can make this web thickness more and more. You can provide the web thickness more and more, or you can call it as a thickening of the web. So these are the some of the preventive measures can be taken to prevent either by local buckling or the web crippling. And since the web crippling occurs only at few sections, it is economical to provide stiffness at these sections. And in case of web buckling, the web may be considered as a strut. In case of a web buckling, the web may be considered as a strut uh, and restrained by the beam flanges. So look at this one, this one. This can be considered as just a strut member. Strut member is nothing but a compression member only. So this is considered as a strut member and is restrained between the flanges. And such idealized strut should be considered at the points of application of concentrated loads or the reaction at the supports, like this. Okay. Then next, the web buckling strength. How to calculate the web buckling strength? It is very important. How we can prevent the web buckling. To prevent the web buckling, first we need to know the web buckling strength, at what load the web of the beam may buckle. Okay, in this web buckling strength, you can refer the IS 800 2007 clause 8.7.3.1, page number 67. There the formula is given for the web buckling strength and how to calculate this web buckling strength. Let us take the web of the beam has buckled like this, and this figure shows the how that load constant means, as we discussed, this web type of failure may take place under the concentrated load or under a reaction points. So the buckling of the web may takes place like this, and it can be prevented just by spreading the load on a wider portion of the flange. Okay, so how that the effective width of the web buckling can be taken. So this figure shows how the loading or the reaction uh, uh, can be spreaded over a longer area. You can see here. So in this case, what happens, a load is been spread. Just look at this figure. This is the reaction points. Okay, so a load is been spread out over a finite length of the web. The load is been spread over a finite length of the web, just as shown in this figure, and this is known as dispersion length. That is this one, b1 plus n1 is known as a dispersion length. It has been spreaded over a longer portion of the web, and this is known as dispersion length. And its theoretical uh, treatment, or you can call it the calculation, is a very complex. Hence empirical formulas based on experiments are used. So theoretical analysis is very difficult, and getting the dispersion length and all, hence it is been taken the empirical formulas based on the experiments. One such assumption is being made here, that is the dispersion length is taken as b1 plus n1, b1 plus n1. So here the dispersion length is b1 plus n1, where b1 represents the stiff bearing length. So that is this one, the stiff bearing length, b1 stiff bearing length, and n1 is the dispersion at an angle of 45 degree. N1 represent the dispersion of 45-degree line. This line has been dotted line, shows the dispersion line, or the what you call as a dispersion of 45-degree line at the mid depth of the section, which has been shown here, and hence the web buckling strength can be calculated by this dispersion length. So hence first we have to calculate the strength, nothing but stress into area. So we need to calculate what is the area, first one. So area is nothing but cross section, because this web is acting as a column, hence we need to calculate the cross sectional area of the column. So cross sectional area into width into thickness. So how much length of the load is being dispersed, that is the dispersion length we need to calculate first, that is b1 plus n1 into thickness of web gives me cross sectional area of the beam, the column. Then the b1, what it represents, stiff bearing length for the flange, and n1 dispersion of load through a web at 45 degree to the level of half the depth of section, and hence n1 is the half of h, where h is the depth of the section. Then finally Fc represents the allowable compressive stress corresponding to web column. Then Pwb, which is represents the web buckling strength. So where the web buckling strength, I'll give you a buckling strength, Pwb is given as b1 plus n1 into tw into fc. p1 plus n1 into t is representing area of dispersion into stress. So stress into area gives you the strength, where T is the web thickness and Fc is the allowable compressive stress corresponding to the assumed web strut. Then the effective length of the strut is been taken, that is effective length here is been given. Look at this one, lambda is the slenderness ratio. The effective length of the strut is, that is Le, is been given 70% of the D, where D is the depth of the strut in between the flanges. So in between the flanges, the depth of the strut is been taken 70% only. So if 70% is effective length, divided by Ry is the radius of gyration. So length by radius of gyration gives you the slenderness ratio. Then the slenderness ratio of the idealized web strut could be written as lambda equal to Le by Ry. Then where Le is the 70% of D, 0.7 into D divided by Ry, where Ry is what? Radius of gyration. So this formula we know in a basic mechanics. So that is root of Iy by A, and Iy is the moment of inertia about y-axis, and this can be easily calculated moment of inertia, that is a dBq by 12 divided by area. So we can calculate moment of inertia Iy, that is dBq by 12. So we can calculate like this. So if we take, see, Iy d so dBq by 12, and this d is nothing but what? D, and b is nothing but thickness. So we get dTq by 12. This is Iy. Okay. Then area, we get depth into thickness. Then if we substitute in formula area, if we substitute, what we get? We get, if we substitute Iy and A, we get finally Tw divided by 2 root 3. Then again if you simplify, then the lambda we get approximately 2.5 times, like this, lambda we get 2.5 into d by Tw. Okay. Then hence the slenderness ratio of idealized strut can be taken as a 2.5 into d by T, like this, 2.5 into d by T. Similarly, the next is a crippling strength, and that is this crippling could also be calculated assuming the empirical dispersion. In this crippling strength, how the crippling strength is being calculated here? So here, assuming, again here also we can assume the dispersion length b1 plus n2, like this, at the reaction point, at the support b1 plus n2, where n2 is the length obtained, and this length is obtained by dispersion through the flange. This dispersion is being taking place through the flange, like this, through the flange to the flange, dispersion through the flange, then to the flange to web connection, flange to web connection, and it is at a slope of 1:2.5. At this slope you have to take, and this is been given in IS 800-2007, how much dispersion length to be taken for the web crippling strength. So this dispersion of the load is been taking place in a ratio of 1:2.5 slope. Okay, so when we take the ratio of 1:2.5 slope, then whatever the length of dispersion we get, that is B1 plus N2. Okay, so again where B1 is a stiff bearing length for the flange and N2 is the length due to dispersion at a flange web junction at a slope of 1:2.5. So remember this figure. So according to this figure, again we have to get the crippling strength of the web. Then TW is the thickness of web. Then FYW is the yield stress of the web material. Then finally we get the crippling strength B1 plus N2 into T into FYW. This is the crippling strength, where FYW is the design yield strength of the web. This is called design yield strength of the web. So you have to remember when you calculate a crippling strength, the load dispersion is to be taken at a slope of 1:2.5. Then we have to calculate the dispersion length, then the dispersion area, the dispersion length B1 plus N2, then the area multiplied by the stress gives you the crippling strength. This is about the web crippling. Try to remember this formula. This is very, very important. So you'll understand this formula when we solve some of the numericals. You will understand this formula. Then last is the deflection criteria. So what is the deflection criteria? So while designing a beams, so how much limits to be taken? So when we get the deflections, so in excessive vibration and excessive deflections are included in the limit state of serviceability. Then the codes usually limits only the deflection. A beam designed to have adequate strength may become unsuitable if it deflects excessively under the loads. Beams that deflect too much may not normally lead to a structural failure, but nevertheless endanger the functioning of the structure. So because of the deflections, what will happen in excessive deflection in the floor, it not only gives the feeling of insecurity, but it also gives the damages to the non-structural components, like cracking up plaster ceilings and all, which has been attached to it. Then the excessive deflection in industrial structures often cause misalignment of the supporting machineries and even cause excessive vibration. And even similarly, high deflections in purlins may cause damage to the roofing materials, and excessive deflection in case of flat roofs results in accumulation of water during the rainstorms called ponding. Hence, some of the limits are being given in a code. So what are those limits? So deflection under serviceability loads of a building component should not impair the strength of the structure or cause damage to finishing. Hence deflections are to be checked for the most adverse but realistic combination of service loads and their arrangement by elastic analysis using a load factor of 1. And IS 800-2007 Table 6 gives the recommended limits of deflection for certain structural members and system. Okay, so these are the some of the limits are being given in a code table. This table 6 gives the limits for deflection for different types of loading, that is vertical loading, lateral loading, and even for other buildings, industrial building and other building. So here the limits are been given, span by 150. These are the maximum deflection limits. So please refer IS 800-2007 table number 6. So we have to prevent the excessive deflection, and that we can check the deflections at last while designing the beams. Then the limits are being given. If we have to check the limits with respect to these limits, that is a deflection of beams with respect to these limits we have to check. And finally we have to say whether the beam is within the deflection limits or beyond the deflection limits, so we can easily conclude at the end. Okay, so with this, uh, I hope you understood these all things, that is a web crippling and web buckling, very very important. Try to understand those things. I hope you understood. Thank you.